Hello, I'm Fatma Aliana Abbas. So my topic is all about the functions of urinary system. So what are the six functions of urinary system? These are the six functions of urinary system. First one is the kidneys filter waste products from the blood. Regulation of blood volume and pressure. Regulation of blood solute concentrations. Regulation of extracellular fluid pH. Regulation of red blood cell synthesis. Regulation of vitamin D synthesis. The kidneys filter waste products from the blood. Nearly 21% of cardiac output is filtered by the kidneys each minute. Fluid and waste are captured by an extensive network of tubes found throughout the kidney. Large molecules, such as proteins, remain in the blood, whereas smaller molecules and ions enter the filtered fluid. Regulation of blood volume and pressure. The kidneys play a major role in controlling the extracellular fluid volume in the body. The kidneys can produce either a large volume of dilute urine or a smaller volume of concentrated urine, depending on the hydration level of the body. Regulation of blood solute concentrations. The kidneys help regulate the concentration of the major ions, such as in A positive, Ci negative, K positive, Ca2 positive, HCO3 negative, and HPO4 2 negative. The kidneys also regulate other solute concentrations such as urea. Regulation of extracellular fluid pH. The kidneys secrete variable amounts of H plus to help regulate the extracellular fluid pH. Regulation of red blood cell synthesis. The kidneys secrete a hormone, erythropoietin, which stimulates the synthesis of red blood cells in the red bone marrow. Regulation of vitamin D synthesis. The kidneys play an important role in controlling blood levels of Ca2 positive by regulating the synthesis of vitamin D. Location and external anatomy of the kidneys. The kidneys are vein-shaped organs. They are retroperitoneal, which means they lie behind the peritoneum and are located on each side of the vertebral column near the psoas major muscles. They are each about the size of a tightly clenched fist. The kidneys extend from the lower portion of the rib cage at the level of last thoracic.
Hello everyone, I am Laura Michelle Gonzalez Ampatuan and I am a second year medtech student, and today we are going to tackle about the internal anatomy and histology of the kidneys and including the structure of nephron. So what are kidneys, by the way? So kidneys are bilateral organs placed retroperitoneally in the upper left and right abdominal quadrants, and it is part of the urinary system. Their shape resembles as a B, where we can describe the superior and inferior poles, as well as the major convexity pointed laterally and the minor concavity pointed medially. So the main function of the kidney is to eliminate excess body fluid, salts, and byproducts of metabolism. So this makes kidneys key in the regulation of acid-base balance, blood pressure, and many other homeostatic parameters. So the other function of kidney is the kidney is very important organ in regards to our body homeostasis. So it participates in vital processes such as circulation of blood osmolarity and pH, regulation of blood volume and blood pressure, and also in the production of our hormones and filtration of foreign substances. Next one is the anatomy. So the anatomy of the kidney is the kidneys have their anterior and posterior surfaces. So the anterior surface faces towards the anterior abdominal wall, whereas the posterior surface is facing the posterior abdominal wall. These surfaces are separated by the edges of the kidney, which are the major convexity laterally and minor concavity medially. So the center of the minor concavity is marked as the hilum of the kidney, where the renal artery enters the kidney and the renal vein ureter leave the kidney. So the kidneys are positioned retroperitoneally, meaning that they are not wrapped with the peritoneal layers the way most abdominal organs are, but rather they are placed behind it. So on the other hand, kidneys do have relation with peritoneum, or precisely with the specific organs that are covered with peritoneum, which are placed directly adjacent to the kidneys. Let's proceed to the external anatomy. So, if we wanted to examine someone's kidneys with ultrasound, we definitely must know where to find them. Since they are located deep retroperitoneally, the easiest way to examine them is from the patient's back. So, the kidneys are located between the transverse process of T12 L3 vertebrae, with the left kidney typically positioned slightly more superiorly than the right. So, this is because the liver and the stomach offset the symmetry of the abdomen, with the liver forcing the right kidney a bit down and the stomach forcing the left kidney a bit up. The superior poles, or the extremities, or T12 of both kidneys, are more medially pointed towards the spine than the inferior poles, or the extremities, or L3. So the hilum of the kidney usually projects at the level of the L2 vertebra. So thus the ureter is seen paravertebrally, starting from the L2 and going downwards. This is the overview of the kidney structure. So a bean-like structure, like the kidney, has two borders, the medial and the lateral. So the lateral border is directed towards the periphery, while the medial border is the one directed towards the midline. So the medial border of the kidney contains a very important landmark called the hilum of the kidney, which is the entry and the exit point for the kidney vessels and ureter. So the most superior vessel in the kidney is the renal vein, which is the exit of the kidney. Just under it is the renal artery that enters in, and under the artery is the exiting ureter. So alternatively, the anterior and to posterior orientation follows the same pattern: renal vein, renal artery, and ureter. So it is important to remember this order of vessels and ducts, since this is the only thing that will make you able to orient the kidney and differentiate the left one from the right when they are outside of the cadaver, or the body of a person or human. So the next one is the kidney tissue is protected by three layers that entirely surround the kidney. So the first one is the fibrous capsule, or renal capsule. So, and the second one is the perinephric fat, or the perirenal fat capsule, and the third one is the renal fascia, which besides the kidney, that also includes the suprarenal gland and its surrounding fat. So outside the fascia is the most superficial layer, a layer of fat tissue called the perinephric fat, and this layer sits posteriorly and posterolaterally to each kidney and separates it from the muscles of the abdominal wall. So let's proceed to the overview of kidney. So in the right kidney anterior surface, we might see the right suprarenal gland, or the highest portion of the superior pole is covered with the right suprarenal gland, or the superior pole, and the superior one half of the anterior surface is in the contact with the layer of peritoneum that separates it from the liver. This potential space that separates the liver from the kidney is called the hepatorenal pouch of Morrison. So it is under normal conditions, and this pouch is empty, but certain pathological conditions such as ascites or hemoperitoneum can cause fluid to collect within the pouch. This can be visualized with ultrasound or CT scan. So at exactly the center of anterior surface, imagine a horizontal stripe that extends from the medial concavity toward the center of the lateral convexity. That is the area of the kidney that is directly touched by the retroperitoneal posterior wall of the descending duodenum. And the lateral part of the inferior pole is directly contracted with the right colic flexures, and also known as the hepatic flexure, which is also retroperitoneal at this part. And the last one is the rest of the inferior pole is associated with the peritoneum of the small intestine, more precisely the jejunum. Let's proceed to the left kidney anterior surface. So, since the abdominal organs are not paired, the left kidney is not related to the same organs as the right kidney. So, in the right kidney, there are left suprarenal gland, stomach, spleen, pancreas, splenic flexure of descending colon, and the jejunum. So, the anterior surface of the left kidney has this, just like the right kidney, the highest part of the superior pole of the left is also covered with the left suprarenal gland. And the inferior portion of the superior pole contacts with the peritoneum of the stomach, or meaty, and spleen, which is the laterally. And just inferior to the stomach and spleen impression is where the left kidney directly contacts the pancreas. And the lateral part of the inferior half of the anterior surface is directly associated with the left colic flexure, also known as the splenic flexure and descending colon. And the medial part of the inferior half and the inferior pole are contracted by the peritoneum of the jejunum. And let's proceed to the posterior surface. So both kidneys are related to certain neurovascular structures and muscles. So they have here the diagram. psoas major muscle, quadratus lumborum muscle, transversus abdominis muscle, and the superior half of each kidney is covered by the diaphragm, which is why the kidney moves up and down during respiration. And the muscular relations of the inferior half are easy to remember by dividing the kidney surface into three vertical stripes, where the medial stripe represents the impression of the psoas major muscle, and the central stripe is the quadratus lumborum, and the lateral stripe is the transversus abdominis muscle. So let's proceed to the internal anatomy. So the parenchyma of the kidney consists of the outer renal cortex and the inner renal medulla. So the main unit of the medulla is the renal pyramid. So there are 8 to 18 renal pyramids in each kidney that on the coronal section look like triangles lying next to each other with their bases directly toward the cortex and the apex to the hilum. So the apex of the pyramid projects medially toward the renal sinus. So this apical projection is called the renal papilla, and it opens to the minor calyx. The minor calyces unite to form a major calyx. Usually there are 2 to 3 major calyces in the kidney, the superior, middle, and inferior, so which again unite to form the renal pelvis, from which the ureter emerges and leaves the kidney through the hilum. So the pyramids are separated by extensions of the cortex called the renal column. So the pyramids contains the functional units of the kidney, the nephrons, which will be discussed later, which filter blood in order to produce urine, which then it's transported through a system of the structure called calyces, which then transport the urine to the ureter. So the pyramids represent the functional tissue that creates urine, whereas the calyces are the beginning of the ureter and transport the urine to it. Let's proceed to the kidney histology. So the kidneys are paired retroperitoneal organs of the urinary system. Their function is to filter blood and produce urine. So each kidney consists of a cortex, medulla, and calyces. So the nephron is the main functional unit of the kidney, in charge of removing metabolic waste and excess water from the blood. Kidney structure is like a bean-shaped organ with a convex lateral surface, concave medial surface, and superior and inferior walls. So the medial surface features the hilum of the kidney, which is the passageway for the renal vessels in the ureter. A connective tissue capsule, which is the renal capsule, is a layer of perinephric or perirenal fat protect the cushion of the kidney. So the capsule contains a layer of contractile cells called myofibroblasts, which make the capsule able to adapt to the constant pressure changes within the kidney. The suprarenal or adrenal gland sits on the kidney superior pole, so it's separated from it by the perinephric fat. But both the kidney and the suprarenal gland are covered by a layer of renal fascia. The kidney parenchyma consists of 2 layers, an outer cortex and inner medulla. They comprise around 1,000,000 urine-producing nephrons. Urine is collected into a system of renal calyces, which is a series of distinctive chambers within the kidney. Calyces gradually increase in size, starting with the minor calyces, which open into large major calyces, which empty into the renal pelvis. From the renal pelvis, the urine passes into your ureter. The portion of the kidney which contains the calyces, renal pelvis, ureter, and renal vessels is called the renal sinus. So the renal cortex is the outer layer of the kidney tissue, so it is darker than its underlying renal medulla because it receives over 90% of the kidney blood supply. The cortex has a grainy appearance, and its most contains ovoid and coiled parts of the nephrons. And the renal medulla appears striped, and it contains vertical nephron structures, and it consists of renal pyramids separated by the projections of the renal cortex or renal columns, and the apices of the pyramids projects towards the renal pelvis and open into the minor calyces via perforated plates on their surfaces or area crabrosa. So each renal pyramid with its surrounding cortical tissue forms a renal lobe, and the renal lobes are further divided into renal lobules. Each lobule consists of a group of nephrons emptying into one collecting duct, and these structures can be observed in the coronal section of the kidney. So let's proceed to the structure of nephron. So the nephron is the functional unit of the kidney. It produces concentrated urine by creating an ultrafiltrate from blood. A nephron consists of 2 main parts, a renal corpuscle and its associated renal tubule system. So renal corpuscles are located in the renal cortex, while their tubular systems extend into the medulla. Depending on their distribution and morphology, there are 2 main types of nephrons in the kidney, which is the cortical and the juxtamedullary. Cortical nephrons have their corpuscles close to the kidney cup, so their tubules are very short, extending only into the upper medulla. The corpuscles of the juxtamedullary nephrons are located close to the corticomedullary border, and their tubular system are much longer, extending deep into the medulla. So, as we should know, nephron is surrounded by a network of capillaries, branches from the renal interlobular arteries enter nephron as the afferent arteriole, it form a capillary glomerulus, then exit the nephron as the efferent arteriole. So the capillary network then continues to surround the nephron's renal tubule system as per tubular capillaries, and it forms the vasa recta around the nephron loop.
Good day to everyone. This is Marcia Barquilia, and for my part, I will be discussing the types of nephrons and the renal corpuscle. Here we have the types of nephrons. Okay. So, these types of nephrons, we have the juxtamedullary nephrons. Okay. So this is the juxtamedullary nephron, and they have the renal corpuscles found deep in the cortex near the medulla. So they have these long loops of Henle, which extends deep into the medulla, which is well adapted for water conservation, and it is only about 15% of these nephrons are juxtamedullary nephrons. The next type of nephrons, we have the cortical nephrons, okay, which have the renal corpuscles that are distributed throughout the cortex. So the loops of Henle in these cortical nephrons are shorter than the previous type of nephron, and which it is much closer to the outer edge of the cortex. Okay, so a nephron this is the nephron, and it is consists of a renal corpuscle, proximal convoluted tubule, a loop of Henle, and a distal convoluted tubule. Next, we will talk about the renal corpuscle. So renal corpuscle is where the filtration portions of the nephron is. Okay, and this consists of the glomerulus and the Bowman capsule. So this is what it looks like, the glomerulus and the Bowman capsule. So glomerulus is a network of capillaries twisted around each other like a ball of yarn. So as you can see here in this picture, looks like a ball of yarn. Instead of yarn, it is made of a network of capillaries. So the fluid filtered in the glomerular capillaries, this one is called the filtrate. Okay. And for the Bowman capsule, it is the indented double-walled chamber surrounding the glomerulus. So here in this picture, this is the Bowman capsule. So the filtered fluid from the Bowman capsule, so the filtered fluid flows into the proximal convoluted tubule region of the renal tubule. Okay. So next we have the Bowman capsule, which consists of two layers. First, we have the parietal layer, which is located here. The outer layer, as you can see in this picture, it is in the outer layer of the Bowman capsule. Okay, it is constructed of a simple squamous epithelial cells, which becomes a cube shape at the beginning of the proximal convoluted tubule. Okay, the next layer, which is the visceral layer, in this picture right here, it is in the inner layer of the Bowman capsule, and it is constructed with a specialized cells which is called the podocytes, okay, that wraps around this glomerular capillaries. So this yellow portion here is the podocytes, and in it is the glomerular capillaries. Okay, so the renal corpuscle have this specific special characteristics that makes it unique and more efficient in filtration, and these are the main functions of the kidneys. Okay, first we have here the fenestrae, okay, wherein the glomerular capillaries are highly permeable, which means permeable, which means that it is can be able will have to pass through the liquid or the gas due to the presence of fenestrae or window. So here in this picture, you can see here, this is the fenestrae. So it does look like an opening in this picture. Okay, so neither large proteins nor blood cells can fit through them. Okay, next we have next function, we have the filtration slits. So in this picture, this is the filtration slits. Okay, so it is between the cell processes of podocytes. Okay, right, this is the podocytes of the visceral layer. Okay, so high pressure. So we have here the an afferent arteriole. So it supplies blood to the glomerulus for filtration. So okay, from the afferent arteriole, so this is the afferent arteriole, so it supplies blood to the glomerulus for filtration. So, and then the efferent arteriole transports the filtered blood here away from the glomerulus. Okay, so this is the process. The afferent arteriole supplies the blood, then filters here in the glomerulus, and then the efferent arteriole takes this filtered blood away from this ball of yarn or the glomerulus. So glomerular capillaries, so this one, have much higher pressure. This is because due to the small diameter of the efferent arteriole than the afferent arteriole. So together with these the structures, it would make up for the filtration membrane. Okay, so filtration membrane consists of a podocyte cell processes, the basement membrane, the capillary endothelium. Okay, so this filtration membrane plays a major role in the urine production. So urine production begins when the filtration membrane filters the blood. Okay, so the filtered fluid enters the lumen or space inside the Bowman capsule. Okay. We have a regulatory structure here, important regulatory structure here, which is called the juxtaglomerular apparatus. Okay. Okay, so the juxtaglomerular apparatus is right here, and to take a closer look, okay, so juxtaglomerular apparatus is located next to the glomerulus. Okay, so it consists of a unique set of afferent arteriole cells and specialized cells in the distal convoluted tubule that are in close contact with each other, and these are the juxtaglomerular cells and the macula densa. So these juxtaglomerular cells are specialized smooth muscles. So this is the just juxtaglomerular cells that cuff around, the afferent arteriole, enters the renal corpuscle. Okay. As for the macula densa here, so it is a group of specialized cells in the section of the distal convoluted tubule where a part of the distal convoluted tubule of the nephron lies between the afferent and the efferent arterioles next to the renal corpuscle. Okay, so secretion of the enzyme renin by the juxtaglomerular apparatus plays an important role in the regulation of the formation of the filtrate formation and blood pressure. Okay, so I guess that's it. That is all for my part today. Okay, thank you for listening and thank you for watching.
Good day everyone, my name is Danica and I will be the one to discuss about the renal tubule. So where does the renal tubule comes from? The renal tubule comes from the nephron, which consists of the renal corpuscle and the renal tubule. And for my part, I will only discuss the renal tubule since the renal corpuscle have already been discussed by Miss Barkilia. And we already knew that the overall information about the nephron, the structures and the types of nephron. A nephron is the basic structural and functional unit of the kidneys that regulates water and soluble substances in the blood by filtering the blood, reabsorbing what is needed, and excreting the rest as urine. So after leaving the renal corpuscle, the filtrate passes through the renal tubule in the following order as shown in the diagram. First is the proximal convoluted tubule, loop of Henle, distal convoluted tubule, and the collecting duct. Again, once the blood is filtered, the resulting fluid is modified to form urine as it passes through each section of the renal tubule. The first section is the proximal convoluted tubule. It is approximately 14 mm long and 60 micrometer in diameter. The proximal convoluted tubule is the longest part of the renal tubule. The wall of the proximal convoluted tubule is composed of simple cuboidal epithelium. The proximal convoluted tubule cells rest on a basement membrane, which forms the outer surface of the tubule. And these cells have many microvilli projecting from the luminal, which is next to the filtrate surface of the cells. And its major functions are the active reabsorption and the secretion. The second section is the descending limb of the loop of Henle. Every loop of Henle has two limbs, the descending limb and the ascending limb. The two limbs both have a thick and thin portion. The first part of the descending limb is similar in structure to the proximal convoluted tubule. The portion of the loop of Henle that extends into the medulla becomes very thin near the bend of the loop. The lumen in the thin part narrows and an abrupt transition occurs from simple cuboidal epithelium to simple squamous epithelium. Like the descending limb, the first part of the ascending limb is thin and made of simple squamous epithelium. Soon, however, it becomes thicker and simple cuboidal epithelium replaces the simple squamous epithelium. So, thin into thicker, simple cuboidal into simple squamous. The thick part of the ascending limb returns toward the renal corpuscle and ends by transitioning to the distal convoluted tubule near the macula densa. The thin segment of the descending limb is composed of simple squamous epithelial cells that have microvilli and contain a relatively small number of mitochondria. The water easily diffuses from the thin segment into the interstitial fluid. The beginning of the distal convoluted tubule is found close to the renal corpuscle in a structure known as the juxtaglomerular complex. The distal convoluted tubule is shorter than the proximal convoluted tubule. The epithelial cells are cuboidal with very few microvilli. However, these cells are smaller and have fewer microvilli. Several distal convoluted tubules connect to a single collecting duct, which is composed of simple cuboidal epithelium. The last section is the collecting duct, which is larger in diameter than the segments of the nephron, form much of the medullary rays and extend through the medulla toward the tips of the renal pyramids. The collecting duct have some microvilli and numerous mitochondria. They actively reabsorb sodium ion, potassium ion, and negative chloride ion.
So let's move on to arteries and veins of the kidneys. So before anything else, system of blood vessels allow the exchange of materials that occurs in the kidneys. The renal arteries branch of the abdominal aorta and enter the kidney. The vessels in order of branching, starting with the renal artery, are the following. First one is the renal artery. The renal artery that delivers approximately 21% of cardiac output per minute. The segmental arteries branch from the renal artery to each portion of the kidney. And also, the interlobar arteries pass between the renal pyramids. Okay, so let's just go ahead and move on to this one so that we can be able to have a better understanding of the arteries in the kidneys. Okay, so first one here is the renal artery. This one delivers approximately 21% of the cardiac output per minute, as I have mentioned earlier. And the segmental artery branch from the renal artery to each portion of the kidney. So as you can see there, the red linings there. That's the segmental artery. The interlobar arteries pass between the renal pyramids. So as you can see there. And the arcuate arteries branch from the interlobal arteries there. And they are between the cortex and the medulla, as you can see there. And the interlobal artery naman branch off from the arcuate arteries and project into the cortex. Okay. And here, the afferent arteries arise from the branch of the aside from the interlobar arteries. The four arteries lead into the glomerular arteries, as you can see there. And the seventh one is the glomerular arteries, or the locations of filtration. So this is where filtrations takes place. Next is different arterioles extend from the glomerular arteries from here to here. There. Oops, I'm sorry. Let's go back there. Okay, so let's move along so we can be able to understand more about what we have discussed on the previous slide. Let's go ahead and tackle about the urine production. There are three processes necessary for urine production. First is the filtration, second is the tubular reabsorption, and tubular secretion. So later on, we will be discussing all three of them so that we can be able to understand more about the urine formation or urine production. Okay, so this is actually the simplest form um, to understand the process of urine production takes place. So this is the one of so let's move along here so we can be able to understand here. Number one here, as you can see there is a blue arrow. It's the filtration. Blue arrow, the one that here is the movement of materials across the filtration membrane into the Bowman capsule to form filtrate. There. Okay, from the Bowman capsule, this is your Bowman, and this is where the filtration takes place. Okay, the second one, this one in the purple arrow, this across the wall of the renal tubule, this is your renal tubule, everyone, into the interstitial fluid by transport process or co-transport. Water is reabsorbed from here, or the orange arrow, across the wall of the renal tubule by osmosis. Well, we already talked about what osmosis is. Water and solids pass from the interstitial fluid into the peritobial capillaries. So here, so you can see peritobial fluid. And the last one here, the green one there is which solids are secreted across the wall of the urinal tubule into the filtrate. So very understandable naman. Okay, so first is the filtration, two is the tubular reabsorption. Next is the tubular secretion. Okay, so there are several measurements of filtration that can be calculated as an indication of proper kidney function. These calculations can measure either rate of whole blood flow or rate of plasma flow. To calculate the rate of filtrate form per minute, that is what we call the glomerular filtration rate, or GRF. You first need to know what percentage of plasma is filtered from the blood so you can be able to get the correct calculation. So this is the calculation of renal flow rates. So renal blood flow amount per minute is 1,176. The calculations are your amount of blood flowing through the kidneys per minute is equal to cardiac output times the percentage of cardiac output that enters the kidney. For example, 560 per minute of blood times 0.21 is equal to 1,126 per minute of blood / minute. For renal flow naman, that's 650 amount of plasma flowing through the kidneys per minute, the same as above. Renal blood flow times the percentage of blood that is plasma. So these are the examples there. Okay. For GFR naman, same pa rin, amount of plasma filtrate that enters the, amount of plasma that enters the Bowman capsule per minute is equal to renal plasma flow times percentage of the plasma that enters the renal capsule. For the urine, that's 1 per minute, or ml. Non-reabsorbed filtrate that leaves the kidney per minute is equal to your GFR filtration rate times percentage of the filtrate that is not reabsorbed into the blood. Okay. So let's go ahead and tackle the filtration membrane. This one, it separates material on the basis of size and charge of the blood components. Thus, the filtration membrane allows water and small molecules to leave the blood while preventing blood cells and most proteins from leaving the blood. Okay, so okay. All right, so let me just go ahead and go back here on the filtration so that we can be able to understand everything. For the filtration process, this is the first process, right? This is a non-selective filtration and separates based only size or charge of molecules. Meaning filtration is comparable to emptying your junk drawer of everything except large permanent items. So meaning to say also filtration does not remove everything in the blood, and also filtration removes only those substances that's small enough to fit through the filtration. Okay. And next is the um tubular reabsorption. So you won't get what do you call this? Um confused of the two. All right. So let's go ahead and talk about filtration pressure. For the for the filtration membrane, there are three forces or pressures that determines the amount of filtered form. These are a combination of these three pressures that is called filtration pressure. Three three pressures contributing to filtration pressures are your GCP, your glomerular capillary pressure. This is essentially the blood pressure inside the glomerular capillaries. It is an outward pressure from the blood pressing on the fenestrated capillary walls. So when we say GCP, the hint there is an outward pressure. Second one is the capsular hydrostatic pressure or CHP. That is also an inward pressure naman that opposes your filtration. This is actually due to pressure from the filtrate fluid into the capsular space. Okay, so again, your GCP is an outward, your CHP is the inward pressure. Third one is the blood colloid osmotic pressure. So this is actually self-explanatory since we have already tackled about osmotic pressure. This is also B cup. Also, this is also an inward pressure that opposes filtration, same as the CHP above. It is due to the osmotic pressure of plasma proteins in the glomerular capillaries. Through osmosis again, these proteins draw fluid back into the glomerular capillary from the Bowman capsule. The yellow one there where the filtration starts, most to siya dito dapita. Okay, so there is also regulation of glomerular filtration rate that we should discuss also so that we can be able to, fully grasp the understanding of how this urine form. So GFR is very stable. It does not significantly change even if systematic blood pressure drops as low as or rises as high as 180. So there are two ways through which the GFR is regulated, by the way. First one is the intrinsic mechanism, referred to as out-regulation and are due to properties inherent to structures of the renal corpuscle. Second is the extrinsic mechanism governed by the autonomic nervous system and particular hormones. Next is the urine concentration mechanism. So as you just have read earlier slides, the kidneys are remarkable at regulating blood composition. The kidney's ability to control the volume and concentration of the urine depends on several factors. First is the counter current mechanisms. Second one is the medullary concentration gradient. And third one is the hormonal mechanism. The counter current mechanism is one where fluid in separate structures flows in opposite directions relative to each other. And on top of that, there are two types of countercurrent mechanisms in the kidney that are critical for either conserving or eliminating water in the body. The countercurrent multiplier in the loop of Henle is responsible for a large percentage of a very high concentration of solutes, while the countercurrent exchanger in the vasa recta in the vasa recta, it maintains the high solute concentration in the interstitial fluid. So again, the countercurrent multiplier is responsible for a large percentage of high concentration of solutes, while this countercurrent exchanger, it in the vasa recta, it maintains the high solute there concentration in the interstitial fluid. That's it.
I am Siti Aina M. Kasan, and my topic is filtration. Filtration is a non-specific process whereby materials are separated based on size or charge. It is the first step in urine production. So, ang filtration ay ang pagtanggal o pagsala sa mga waste products from the blood by the kidney. They are excreted from the body through urine. The importance of filtration is indicated by the large percentage of cardiac output or blood sent through the kidneys each minute. So, this percentage of cardiac output that flows through kidneys is what we call renal fraction. There are several measurements of filtration that can be calculated as an indication of proper kidney function. So, these calculations can measure either the rate of whole blood flow or rate of plasma flow. To calculate the rate of whole blood flow through the kidneys, called renal blood flow rate, two pieces of information are necessary. First is the renal fraction or 21%, and the second is the cardiac output or 5,600 milliliter per minute. So, this is the equation used for rate of whole blood flow. To calculate the rate of plasma flow through the kidneys, called renal plasma flow rate, we must account for the percentage of whole blood made up by plasma, which is approximately 55%. So, this is the equation used for the rate of plasma flow. To calculate the rate of filtrate formed per minute, called the glomerular filtration rate or the GRF, you first need to know what percentage of plasma is filtered from the blood. This is called the filtration fraction. The filtration fraction is approximately 19%. Thus, to calculate the GRF, this is the equation used. Filtration membrane, it separates materials on the basis of size and charge of the blood components. So, these are essentially microporous barriers of polymeric, ceramic, or metallic materials which are used to separate dissolved materials or solutes, colloids, or fine particulates from solutions. So, these are the several structures make up the filtration membrane. First is the fenestrated glomerular capillaries. Second is the basement membrane between the capillary wall and the visceral layer of the Bowman capsule. And the last one is the podocytes of the visceral layer of the Bowman capsule. Filtration pressure is equal to the glomerular capillary pressure minus the capsular hydrostatic and blood colloid osmotic pressure. So, infiltration pressure forces fluid and all solutes smaller than a certain size through a membrane. Blood pressure forces water and dissolved blood components through the pores of the capillaries basement membrane, and on through the slit membranes between pedicels. These are the three pressures contributing to filtration pressures. These are the glomerular capillary pressure or the GCP, the capsular hydrostatic pressure or CHP, and the blood colloid osmotic pressure or the BCOP. Glomerular capillary pressure, the blood pressure within the glomerulus moves fluid from the blood into the Bowman capsule. So this is the driving force for filtration, and it is opposed by the hydrostatic pressure in Bowman's capsule and the colloid osmotic pressure exerted by the plasma proteins. Capsular hydrostatic pressure, the fluid pressure inside the Bowman capsule, moves fluid from the Bowman capsule into the blood. So this is a back pressure that opposes filtration. As the filtrate is forced into the capsular space, it meets two forms of resistance: the wall of the capsule and the fluid that has already filled the renal tubule. As a result, some filtrate is pushed back into the capillary. Blood colloid osmotic pressure, produced by the concentration of blood proteins in the glomerular capillaries, moves a fluid from the Bowman capsule into the blood by osmosis. So, this is the pressure created by the concentration of colloidal proteins in the blood. Its effect on capillary exchange accounts for the reabsorption of water.
So regulation of glomerular filtration rate or the GFR. So the GFR is very stable. It does not significantly change even if systemic blood pressure drops as low as 90 mmHg or rises as high as 180 mmHg. There are two ways through which the GRF is regulated. First is the intrinsic mechanism and second is extrinsic mechanism. First is intrinsic mechanism, also known as autoregulation. So autoregulation is achieved through processes. First is the myogenic mechanism. Second is the tubule-glomerular feedback. Smooth muscle cells act as the stretch receptors. These stretch receptors detect changes in the blood pressure. Elevated blood pressure causes increased stretch of the smooth muscle cells in the wall of the afferent arteriole. On the other hand, smooth muscle cells in the wall of the afferent arteriole relax when the blood pressure decreases. Relaxation of the smooth muscle cells causes vasodilation of the afferent arteriole. In this way, blood supply of the glomerulus and thus GFR fluctuates very little even when the mean arterial pressure changes. So the second one would be extrinsic mechanism. In severe conditions such as hemorrhage or dehydration, the mean arterial pressure can drop below 90 mmHg, and the sympathetic nervous system causes a dramatic decrease in renal blood flow and GFR to maintain homeostatic blood pressure. However, small changes in the sympathetic stimulation have a minimal effect on the renal blood flow and filtrate formation. As a consequence, kidney tissues can be damaged and thus unable to perform their normal functions if blood flow is not re-established. Therefore, shock should be treated quickly. On the other hand, reduced blood flow to the kidneys during stress or shock is consistent with the homeostasis.
Good day, my name is Jadida Dididaagan and I'm here to report about tubular reabsorption and reabsorption in the proximal convoluted tubule. Tubular reabsorption is the transport of water and solutes from the filtrate into the blood. The process of tubular reabsorption entails nearly every type of cell transport mechanism. Recall that osmosis is the movement of water toward solutions with higher solute concentration or high osmotic pressure. Solute movement is quite often through diffusion across the renal tubule cell. Diffusion is the net movement of solutes down their concentration gradient. Proper tubular reabsorption is critical in preventing the body from becoming overly dehydrated and deficient in important materials. The filtrate leaves the lumen of the Bowman capsule and flows first through the proximal convoluted tubule into the loop of Henle and the distal convoluted tubule, and then finally into the collecting ducts. Inorganic salts, organic molecules, and about 99% of the filtrate volume leave the renal tubule and enter the interstitial fluid. Because the pressure is low in the peritubular capillaries, these substances enter the peritubular capillaries and flow through the renal veins to enter the general circulation. Reabsorption in the proximal convoluted tubule. The proximal convoluted tubule is the site of the majority of the reabsorption. The mechanism underlying reabsorption can be better understood by considering the cells found in there. The cells of the proximal convoluted tubule have numerous microvilli, which dramatically increase the surface area available for reabsorption. To establish the portion of each proximal convoluted tubule where a particular process for reabsorption occurs, these portions are named. The portions of each cells are the following: basal membrane, apical membrane, and lateral surface. Basal membrane is the basal membranes from the outer wall of the renal tubules. The apical membranes make up the inside surface of the renal tubule wall. It is the apical membrane of the proximal convoluted tubule that houses of the microvilli, carrier proteins that transport amino acid, glucose, and other solutes are located within the apical membrane, which separate the lumen and the proximal convoluted tubule from the cytoplasm of the cells of the proximal convoluted tubule. The lateral surfaces bind the renal tubule cells to adjacent cell in the renal tubule. So the reabsorption of most solutes is linked into the diffusion of Na plus into the cell of the proximal convoluted tubule. There is a steep concentration gradient for Na plus from the filtrate into the cytoplasms of the cells and proximal convoluted tubule. This concentration gradient is established by active transport of Na plus across the basal membrane of the cells of the proximal convoluted tubule. The number of carrier proteins limits the rate at which a substance can be transported. For example, the high blood glucose in someone with untreated diabetes mellitus can lead to such high glucose levels in the filtrate that not all of it can be removed by glucose transport proteins. The excess glucose remains in the filtrate and becomes part of the urine. Some solute also diffuse from the lumen of the proximal convoluted tubule into the interstitial fluid by moving between the cells across their lateral surfaces. So, when the concentration of the solutes in the lumen becomes higher than the interstitial fluid, these solutes will diffuse between the tubule cells into interstitial fluid. Example of solutes that diffuse between tubule cells of the proximal convoluted tubule include K+, Ce2+, and Mg2+. These solutes are reabsorbed by diffusion, even through the Same ions are also sometimes reabsorbed by same-port processes. As solute molecules are transported out of the filtrate, water also moves by osmosis out of the filtrate. By the time the filtrate has reached the end of proximal convoluted tubule, its volume has become reduced by approximately 65%.
Hello everyone, I am Patrice Jane Hudaya, and I'm going to discuss the loop of Henle and its two sections, which are the descending and ascending sections. The loop of Henle is deemed to us called counter-current multiplier system. So with the counter-current multiplier systems, this means two things. Firstly, the counter-current part means that fluid within the section is going into opposite directions, and the multiplier system part means that it's creating a very steep solute gradient in the medulla. Now let's take a look at this illustration. As you can see, it is made up of two limbs here. Now this part on this side is called the descending limb, and that is going down into the medulla section of the kidney. And then over here, we've got the ascending limb, which is coming back out of the medulla section of the kidney. So in terms of the flow of fluid, a filtrate is coming out from section 2 of the proximal convoluted tubule, and it's moving down into this descending limb of the loop of Henle, and it will move all around and it will come up with ascending limb, and it will move into section 4, which is then a distal convoluted tubule. So this is then the countercurrent part of the system. This section here, the filtrate is moving downwards, and then up here at the ascending limb is moving in the opposite direction. It's coming back up. But before we go beyond this discussion, let's talk a little bit about the concentration of the filtrate as we're coming through into this loop of Henle. So up here, where the first arrow is, the filtrate is coming from the proximal convoluted tubule, and in terms of its concentration, it is about 300 milliosmoles. It is also made up of combination of lots of different things, such as sodium ions, chloride ions, and water. Now let's talk about its permeability. In descending limb, water is able to move across the membrane. Ions, sodium and chloride ions, are not able to move across the membrane. Now, for the ascending limb, in terms of the permeability, it is the exact opposite. So water is not able to cross the membrane. However, ions on this limb are able to cross the membrane. So, the descending limb is permeable to water but not permeable to ions, and the ascending of the loop of the Henle is permeable to ions but not to water. Now, in terms of key things that are happening, the sodium ions and the chloride ions are actively pumped across the membrane into the interstitial fluid here in the medulla, so obviously it requires ATP. This means that the medulla increases in solute concentration and the filtrate starts to decrease in concentration. And as we're coming up this ascending limb of the loop of Henle, more and more ions are being pumped out, and therefore it becomes less and less concentrated as we're going up. So we've got some sodium ions and chloride ions, and they are being pumped across the membrane here into the medulla. So this means
this medulla section becomes more concentrated as these ions moves out, and the filtrate, as it's coming further and further up this ascending limb, it becomes less and less concentrated. So here, the filtrate is very low concentration, and it is about 100 milliosmoles. Now let's go back to the descending limb. With this one, the main thing here is that the water moves out of the loop of Henle here, and it will go into the medulla. And it does this very simply by osmosis. It could do it by osmosis because previously we pumped out all of these ions from the ascending limb into the medulla. We've got then a very, very high solute concentration. And remember that osmosis means water moves from a low solute concentration to a higher solute concentration through a semi-permeable membrane. So water is just passively moving from this descending limb into the medulla section here. As this happens, the medulla starts to then decrease in concentration because we are filling it more water. And the filtrate will increase in concentration because we're taking water out here, but all of these ions here that we haven't yet pumped out are still in this section here. That means that down here at the bottom of our loop of Henle, this filtrate has a very high concentration. So remember, this is because we started with the filtrate at 300 filled with sodium chloride and water. To begin with, we pumped out quite a lot of the water so that we've still got a little bit of water, but we've also got very, very high concentrations of this sodium and chloride because that hasn't been pumped out here because the descending limb is impermeable to these ions. It is a very high concentration filtrate down here. As we then move up to the ascending limb, these ions are then pumped out actively through pumps into the medulla section here, which means that as it's passing up here, the filtrate becomes a lower concentration and it is around 100 milliosmoles. The other thing is obviously because we are actively pumping lots of things out and osmosis is taking water out, the volume of filtrate again is decreasing. So when we first look at the proximal convoluted tubule, we had 180 liters coming in from the glomerula filter. This is again a section where quite a lot of the components in the filtrate are absorbed back into the body again. So the concentration does change, but also the volume of filtrate will also change as we go to this section here. So by the end of this ascending limb up here, we've got low concentration filtrate, about 100 milliosmoles. So in terms of what that is then a what do we call the hypotonic solution because it has a lower concentration than the fluid surrounding it in the interstitial fluid. So in the filtrate is now in a lower concentration than their surrounding fluid. Next is we're gonna talk about the reabsorption in distal convoluted tubule and collecting duct. The main thing here in the distal convoluted tubule and the collecting duct is having a look at the blood solute concentration, and these two sections will then help to basically troubleshoot this blood solute concentration. So we're going to have a look at two different scenarios. first one is if the blood solute concentration is too low. These two areas will become more permeable to water, and the water will be reabsorbed into the nephron. This is primarily because the solute concentration in your surrounding tissues in your blood is too low, so it's got too much water in it. Therefore, the water is reabsorbed back into these areas here. That then means that your final filtrate will decrease in concentration, so it becomes more dilute. The opposite, if your blood solute concentration is too high, so it doesn't have enough water in it. Water is then absorbed into your blood, and this actually is controlled by a hormone secreted by your pituitary gland called antidiuretic hormone, which will also be seen as ADH. So, ADH makes the walls of the distal convoluted tubules and the collecting duct more permeable. So this means that water is able to move out and it can go into your blood to decrease the solute concentration of your blood, thereby increasing the concentration of the final filtrate, so you have a more concentrated urine that is produced in the end.
Good day everyone. So for today's video, I'm gonna discuss about the changes and the concentration of urea and other solutes in the nephron. So one of the nephron's major functions is to remove waste from the body. So the nephrons work through a two-step process. The glomerulus filters your blood, and the tubule returns needed substances to your blood and removes waste. So each nephron has a glomerulus to filter your blood and a tubule that returns needed substances to your blood and pulls out additional waste. So the reabsorption and loop of Henle. So the wall of the thin segment of the descending limb of the loop of Henle is permeable to water and to a lesser extent to solutes. So the interstitial fluid in the medulla of the kidney and the blood and the vasa recta have a high solute concentration. So the water therefore moves by osmosis from the tubule into the interstitial fluid and into the vasa recta. An additional 15% of the filtrate volume is reabsorbed. To a lesser extent, solutes diffuse from the vasa recta and interstitial fluid into the tubule. So, the thin segment of the ascending limb of the loop of Henle is not permeable to water but is permeable to solutes. The solutes diffuse out of the tubule and into the more dilute interstitial fluid as the ascending limb projects toward the cortex. So the solutes diffuse into the descending vasa recta. So the tubular secretion. So it is the transfer of materials from peritubular capillaries to the renal tubular lumen. So when we say lumen, that is the inside space of a tubular structure such as an artery or intestine. So it is the opposite process of reabsorption. So this is the secretion is caused mainly by active transport and passive diffusion. So the use of tubular secretion is one of many steps in the process of filtering blood to produce liquid waste in the form of urine. So within the excretory system of many organisms, this is important for both waste removal and acid-base balance. Usually only a few substances are secreted and are typically waste products. So urine is the substance left over in the collecting duct following reabsorption and secretion. So the mechanisms of secretion. So the mechanism by which secretions occurs are similar to those of reabsorption. However, these processes occur in the opposite direction, which are the passive diffusion and the active transport. So the passive diffusion are the movement of molecules from the peritubular capillaries to the interstitial fluid within the nephron. So the second one is the active transport, which is the movement of molecules via active base pumps that transport the substance through the renal epithelial cell into the lumen of the nephron. So the renal secretion is different from reabsorption because it deals with filtering and cleaning substances from the blood rather than retaining them. So the substances that are secreted into the tubular fluid for removal fluid the body include potassium ions, hydrogen ions, ammonium ions, creatinine, urea, some hormones, and some drugs or the penicillin. That's all. Thank you and God bless.
Hi, I'm Yasser Makagan. Now I'm going to discuss the urine concentration mechanism. So urine concentration mechanism is the kidney are able to produce urine with concentration ranging from a minimum of 65 milliosmoles per kilogram to a maximum of 1200 milliosmoles per kilogram, while maintaining the extracellular fluid concentration very close to 300 milliosmoles per kilogram. But maybe you wonder how can our kidney move such a large amount of volume of fluid from the blood into the filtrate and then back into the blood. So the kidney's ability to control the volume and concentration of the urine depends on several factors. First is the countercurrent mechanism. Second is medullary concentration gradient and hormonal mechanism. So countercurrent mechanism is one where fluid in separate structures flows in opposite directions relative to each other as the fluid pass by each other materials. Each other materials can be exchanged between the fluids. There are two types of countercurrent mechanism in the kidney that are critical for either conserving or eliminating water in the body. So the two types of countercurrent mechanism are the countercurrent multiplier and the countercurrent exchanger. So first let's discuss the countercurrent multiplier. So the countercurrent multiplier in the loop of Henle is responsible for a large percentage of very high concentration of solutes that is found in the interstitial fluid within the medulla of the kidney. So the permeability changes in the loop of Henle are responsible for its role as the countercurrent multiplier. So the second is the countercurrent exchanger. So in the in the vasa recta maintains the high solute concentration in the interstitial fluid. Because the flow rate and blood pressure in the vasa recta are so slow and very low, the blood and the interstitial fluid are always in equilibrium and solutes are not carried away from the interstitial fluid by the blood in the vasa recta. So that's all. Thank you.
Good day everyone. I am Alima Mahmoud and the next topic we will tackle about is the countercurrent mechanisms medullary concentration gradient. So to create and maintain the medullary concentration gradient, the following processes occur. So here are the 1A and 1B. The first 1A is the countercurrent multiplier. So, countercurrent multiplier as filtrate travels through the descending line of the loop of Henle. Water moves across its simple squamous epithelium by osmosis toward a higher solute concentration in the interstitial fluid. So, here in countercurrent multiplier, as we discussed, this osmosis of water out of the filtrate causes the filtrate to become highly concentrated. Then, as the filtrate begins to move through ascending line, this increases the concentration of the interstitial fluid even more. So, in countercurrent exchanger, the vasa recta supply blood to the kidney medulla and they remove excess water and solutes from the medulla without changing the high concentration of solutes in the medullary interstitial fluid. So, in the case of countercurrent exchanger, the vasa recta have a countercurrent mechanism because blood flows the opposite direction back toward to the cortex. So as blood flows back toward the medulla, water moves out of the vasa recta. So let us proceed to number 2, the urea cycling. Urea is responsible for a substantial part of the high osmolality in the kidney medulla. Due to their histology, the walls of descending lines of the loops of Henle are permeable to urea. Thus, urea diffuses into the descending limes from the interstitial fluid. As you can see in the picture, this shows how urea recycled. However, due to their histology, the ascending limes of the loop of Henle and the distal convoluted tubules are impermeable to urea. So the urea remains in the loop of Henle until it reaches the collecting ducts, which are permeable to urea. Therefore, urea is recycled from the interstitial fluid into the descending limes of the loop of Henle. To summarize, several key events occur in the renal tubule to establish and maintain a high medullary solute concentrations. So letter A, sodium ions and other solutes are actively transported into the interstitial fluid of the medulla, maintaining a high medullary osmolarity. B. Because blood flows sluggishly and there is low blood pressure in the vasa recta, solutes are not washed away from the medulla. Letter C. Much urea returns to the medulla from the collecting duct rather than exiting with the urine. Summary of urine formation. So this photo illustrates how urine formed. Summary of urine formation. The kidneys filter unwanted substances from the blood and produce urine to excrete them. There are 3 main steps of urine formation. So we have the glomerular filtration, reabsorption, and secretion. So these processes ensure that only waste and excess water are removed from the body. So this glomerular filtration, it creates a plasma-like filtrate of the blood, while the tubular reabsorption removes useful solutes from the filtrate, returns them to the blood. The tubular secretion removes additional waste from the blood and adds them to the filtrate. Then the last one, which is the water conservation, removes water from the urine and returns it to the blood, concentrates waste. And that's all. Thank you.
Good day everyone. I am Sitia Ashabini Tumarhum from BS Medical Technology, second year college. So today I will be discussing to you all about hormonal mechanisms. Let us find out first what are hormones. So a hormone is a chemical messenger that enables communication between cells. Hormones are secreted by the glands of the endocrine system and they serve to regulate numerous other systems and processes, including reproduction and development. So hormones are chemical messengers that are secreted directly into the blood, in which carries them to organs and tissues of our body, and to exert their functions. They are secreted from the endocrine glands in the body, and also the glands is ductless. So that is why hormones are secreted directly into the blood stream rather than by way of ducts. There are also two types of hormones, which are the water-soluble hormone and the lipid-soluble hormone. So the water-soluble hormone is a lipophobic hormone that binds to a receptor on or within the plasma membrane to initiate an intracellular signaling cascade. The receptors for these hormones need to be localized to the cell's plasma membranes. Following an interaction with the hormones, a cascade of secondary effects within the cytoplasm of the cell is triggered, often involving the addition or removal of phosphate groups to cytoplasmic proteins, changes in ion channel permeability, or an increase in the concentrations of intracellular molecules that may act as secondary messengers, such as cyclic AMP. So the examples of a water-soluble hormone are adrenaline, noradrenaline, thyroid-stimulating hormone or THS, and human growth hormone or HGH. The other one is the lipid-soluble hormone, which is a lipophilic hormone that passes through the plasma membrane of a cell, binds to an intracellular receptor, and changes gene expression. The majority of lipophilic hormone receptors are transcription factors that are either located in the nucleus waiting for the steroid hormone to enter and activate them. Upon binding by the hormone, the receptor undergoes a conformational change, and the receptor together with the bound hormone influence transcription, either alone or in association with other transcription factors. Lipid soluble hormone includes testosterone, estrogens, progesterone, aldosterone, and cortisol. So what is hormone signaling? So the glands of the endocrine system secrete hormones directly into the extracellular environment. And then yung hormones is mag-diffuse siya sa bloodstream through capillaries, and then ma-transport siya sa target cells through the circulatory system. It will then allow hormones to affect the organs and tissues of our body far from the site of production, or to apply systematic effects to our whole body. The hormone-producing cells is typically specialized and reside with a within a particular endocrine gland, such as thyroiditis in the thyroid gland, and hormones exit their cell of origin through the process of exocytosis or by membrane transport. These are the steps of hormonal signaling. So first is the biosynthesis of a particular hormone in a particular tissue. Second, storage and secretion of the hormone. Third, the transport of the hormone to the target cells, tissues, or organs. Fourth, the recognition of the hormone by an associated cell membrane or an intracellular receptor protein. Fifth, relay and amplification of the received hormonal signal via a signal transduction process. Lastly, is the potential feedback to a hormone producing cell. So those are the 6 steps of hormonal signaling. So let us now discuss the 3 classes of hormones, which are the peptide hormones, lipid-derived hormones, and monoamine hormones. So the peptide hormones are modified amino acids or short or long chains of amino acids. Also, they can contain carbohydrate moieties. So peptide hormones consist of short chains of amino acids such as vasopressin that are secreted by the pituitary gland and regulate osmotic balance, and for the long chains such as insulin that are secreted by the pancreas, which regulates glucose metabolism. Also, some peptide hormones contain carbohydrates, side chains, and are termed glycoproteins, such as follicle-stimulating hormone. All peptide hormones are hydrophilic and are therefore unable to cross the plasma membrane alone. Next is the lipid-derived hormones, which is a steroid hormone that contains lipid synthesized from the fatty acid chains of phospholipids found in the plasma membrane. It is a hormone that are produced from lipids such as linoleic acid and arachidonic acid. Steroid hormones, which form the majority of lipid hormones, are derived from carbohydrates. For example, the testosterone is produced primarily in the testes and plays a key role in development of the male reproductive system. Also, eicosanoids are derived from fatty acids in the plasma membrane, not like the other hormones. Eicosanoids are not stored in the cell. They are synthesized as required. Both are lipophilic and can cross the plasma membrane. Last is the monoamine hormones, which is a hormone derived from aromatic amino acids such as phenylalanine, tyrosine, and tryptophan. An example for this is the tryptophan-derived melatonin that is secreted by the pineal gland regulates sleep patterns.
My name is Shafa Muhammad Kasim, and my topic is all about the renin-angiotensin-aldosterone hormone mechanism. The renin-angiotensin-aldosterone mechanism is initiated under the low blood pressure conditions. When blood pressure decreases, cells of the juxtaglomerular apparatuses in the kidneys secrete the enzymes renin, The kidneys detect the low blood pressure when juxtaglomerular cells detect reduces stretch of the afferent arteriole. In addition, the macula densa cells signal the juxtaglomerular cells to secrete renin when the sodium ion or the Na positive concentration of the filtrate drops. ACE converts angiotensin 1 to angiotensin 2, which is shown in the picture to the right. Angiotensin 2 is a potent vasoconstricting hormone that increases peripheral resistance, causing blood pressure to increase. However, angiotensin 2 is rapidly broken down, so its effect lasts for only a short time. Angiotensin 2 also increases the rate of aldosterone secretion, the sensation of thirst, salt appetite, and ADH secretion. When we say aldosterone, aldosterone is a steroid hormone secreted by the cortex of the adrenal glands, which is shown in the picture. Aldosterone binds to its receptor in both the distal convoluted tubules and the collecting ducts. Aldosterone molecules diffuse through the plasma membranes and bind to their nuclear receptors. The binding of aldosterone to its receptor increases the synthesis of the sodium ion or Na positive to potassium or K positive pump and other Na transport proteins. The sodium ion or Na positive to potassium or K positive pump increases the reabsorption of Na positive and the secretion of K positive across the basal membrane of tubule cells, while the other Na positive transport proteins increase the transport of Na positive across the apical membrane of tubule cells. As a result, the rate of Na positive reabsorption increases. Simultaneously, because of the action of Na positive to K positive pump, K positive secretion increases rather than its reabsorption, as you can see in the picture. Reduced sodium ion or Na positive reabsorption keeps the concentration of Na positive in the distal convoluted tubules and the collecting ducts elevated. Because the concentration of filtrate passing through the distal convoluted tubules and the collecting ducts has a greater than normal concentration of solutes, water's capacity to move by the osmosis from the distal convoluted tubules and the collecting ducts is diminished, urine volume increases, and urine has a greater concentration of Na positive. Because increases in the number of Na positive to K positive pumps increases the rate of potassium or K positive secretion, increase in blood K positive levels stimulate aldosterone secretion. Conversely, decreases in blood K positive levels decrease aldosterone secretion, as shown in the picture.
Okay, so good morning, ma'am. I'm Michael Dominic Sinietes, and as I start this part of our report, so first, let's pray. So, our Father art in heaven, okay, so my discussion in this afternoon or mornings is about antidiuretic hormone mechanism. So, what is the antidiuretic hormone mechanism? So, ADH or antidiuretic hormone mechanism is hormone of the supratic nucleus of the hypothalamus produce antidiuretic hormone, or as I say, it is a ADH. So ADH is also known as vasopressin, which is stored in the posterior pituitary gland. ADH is released into the blood from the posterior pituitary. Then cells called osmoreceptor cells in the supraotic nucleus are very sensitive to even slight changes in the osmolality of the interstitial fluid. So if the osmolality of the blood and interstitial fluid increases, so this cell stimulates the ADH secreting neurons. So as we can see here in this illustration, so these are the vasopressin and then the vasoconstriction, which is here, and then the blood pressure. So this thing is the blood pressure, and then the antidiuresis, and then prevents making too much urine. So this is the water retention. So next, then the EDH stimulates water absorption by stimulating in secretion of water channels or aquaporins into membranes of kidney tubules. So it is also called vasopressin, which is transported from the supply to posterior pituitary and released in response to increase in the plasma osmolality and decreases in blood pressure. So as you can see here, so this is the tubulin, and then this is the vas recta, and the EDH or vasopressin. So this is where the EDH located. Wait, so this is where the EDH located. So as we can see here, this is a octagon. I think it's a hexagon. So here, so the EDH will transport into the EDH receptor, and then resulting into transporting here, and then this is the aquaporin, and then the protein A, then aquaporin 3. So this is where the mechanism happens. So next, so what will happen if the body will experience insufficient ADH secretion? So this condition is called diabetes insipidus. So the word diabetes refers to the production of a large volume of urine, and the word insipidus means the urine is clear, tasteless, and dilute. People who secrete insufficient ADH often produce 10 to 20 liters of urine per day and develop major problems such as dehydration and ion imbalances. So in contrast to diabetes insipidus, so the diabetes mellitus refers to the production of a large volume of urine that contains a high concentration of glucose. So when people have this kind of disease, so he or she may suffer dehydration because your body has ion imbalances, which makes him or he here feels thirsty. So next, so alerting from this diabetes insipidus is an uncommon disorder that causes an imbalances of fluids in the body. So these imbalances leads you to produce large amount of urine. So it also makes you very thirsty. So like I said before earlier, so it makes you thirsty even you have something to drink. That is why people will have this disease well urinating 10 to 20 liters of urine per day because of thirstiness. So if a person become thirsty, so he or she will eventually drink water. So that is why. And then the diabetes insipidus is a rare condition where you pee a lot. So like I say, you will pee a lot and often feel thirsty. So the two main symptoms of diabetes insipidus are first, extreme thirsty. So it also called polydipsia, and then peeing a lot even at night. So polyuria. So these are the two symptoms of diabetes insipidus. So this should be seek immediately in a physician or a doctor if you have this kind of disease, because it's not a normal one in a person, because in a person feel thirsty even though your body has the amount of water needs. So it is an abnormal mechanism that is happening in your body that is should be cured. So next. So in summary, the antidiuretic hormone is also called vasopressin, and it promotes water retention by kidneys, and then secretion rate changes in response to alternation in blood, and then uh, in blood osmolality and blood volume. So and the most important thing, if you if you know about the ADH, so if a person lack of ADH secretion, it can cause a diabetes insipidus. So like I tackled earlier, the two types or the two causes of lack of ADH secretion is when you feel thirsty and peeing a lot. So that's all for my report. And now, as I end my part, I'm Michael Dominic Signetes, and thank you for this opportunity, and Merry Christmas and Happy New Year. Thank you and God bless us all.
I'm Jana M. Pautin, and I will be discussing the production of concentrated urine. So concentrated urine or also called as hyperosmotic urine, means that the osmolality is greater than that of blood. When there is a water deficit in our body, our kidney forms a concentrated urine by continuing to excrete solutes while increasing water reabsorption and decreasing the volume of urine formed. In hyperosmolality of medullary interstitium, 50 to 60% of hyperosmolality is contributed by the countercurrent, multiplier, and exchange system, which will be discussed later. So, the role of urea in the production of concentrated urine is about 40 to 50%. So, people who ingest a high protein diet yielding large amount of urea as a nitrogenous waste product can concentrate their urine much better than those people whose protein intake and urea production are low. Malnutrition is one example of low urea concentration in the medullary interstitium and is considered as impairment of urine concentrating ability. So, an obligatory urine volume in a normal 70-kilogram human must excrete about 600 millismoles of solute each day. Then, the human kidneys can produce maximal urine concentration of 1,200 to 1,400 millismoles per liter, or 4 to 5 times the osmolarity of plasma. Then, if the maximal urine concentrating ability is 1,200 millismoles per liter, then the minimal volume of urine that must be excreted, called the obligatory urine volume, can be calculated as 600 millismoles per day divided by 1,200 millismoles per liter equals to 0.5 liter per day. Also, dehydration develops if drinking seawater. Why? Because for every liter of seawater drunk, 2 liters of urine volume would be required to rid the body of 1,200 millismoles of sodium chloride, ingested in addition to other solutes such as urea. This would result in a net fluid loss of 1 liter for every liter of seawater drunk, explaining the rapid dehydration that occurs in shipwreck victims who drink seawater. So we have two types of countercurrent mechanisms to determine urine concentration and its volume. So we have the countercurrent multiplier and the countercurrent exchanger.
So countercurrent multiplier is the interaction between the flow of filtrate through the ascending and descending limbs of the long nephron loops of juxtamedullary nephrons. So here is the diagram, sample diagram of a nephron loop of Henle. This one right here is the descending limb. Here in descending limb, the filtrate is going downward. This arrow going down. Descending limb is freely permeable to water, which passes out of the filtrate into the hyperosmotic medullary interstitial fluid, and its filtrate osmolality increases to 1,200 millismoles. Then on this side is the ascending limb. Its filtrate is going upward. This arrow going up. So it is impermeable to water and its filtrate osmolality decreases to 100 millismoles. Then the next one is the countercurrent exchanger. It is the flow of blood through the ascending and descending portion of the vasa recta. So as you can see here in this diagram, the blood from the efferent arteriole, this one going down, is entering in the vasa recta. And when the blood leaves the vasa recta, the blood will then enters to the vein. Mugawas siya dera, then moadto din siya sa vein. So this flow of blood, the descending and ascending limb of vasa recta is known as the countercurrent exchanger. So the antidiuretic hormone, ADHD, or also known as arginine vasopressin, is a chemical produced in our brain that causes the kidneys to release less water. Decreasing the amount of urine produced, a high ADH level causes the body to produce less urine, and a low level results in a greater urine production. Did you know that the amount of ADHD in our body is higher during the night? Because this helps prevent urination while we are sleeping. But if the levels of ADH levels remain low during the night, the body will produce large amount of urine. So urination during the night is more likely. So moving on to produce more concentrated urine, we must move on to the other step or the final step, which is the collecting of tubules. So collecting of duct is the final component of the kidney to influence the body's electrolyte and fluid balance. It is under the control of ADH or the antidiuretic hormone, which I already discussed. So the collecting ducts determine the final concentration and volume of urine. So it conducts filtrate through the osmolarity gradients, and more water exits the filtrate by the osmosis. So we have the three major segments of collecting duct. So the three major segments of the collecting duct serve three different functions in the urinary concentrating mechanism. The main function of the cortical collecting tubules, the first one, is to raise the fractional solute contribution and absolute concentration of urea in fluid that it delivers to the outer medullary collecting ducts. Then the function of the outer medullary collecting duct, the second one, is to raise further the absolute intraluminal urea concentration. Finally, the inner medullary collecting ducts, the last one, the third one, it has two major functions in urinary concentration. First, it adds net urea to the papillary interstitium, and second, it allows the generation of maximally concentrated urine due to the osmotic water equilibration. Indeed, the urine osmolality can rise to levels higher than the papillary interstitial osmolality as a consequence of inequalities of the reflection coefficient of urea and sodium chloride. That's all. Thank you. Now we will move to the production of dilute urine, which will be discussed by Rial, Miss Rial.
Hello everyone, I am Almira Muriel and good morning to you, Mom Celeste. So our topic for today is production of dilute urine. If ADH is not present or its concentration is low, the distal convoluted tubules and collecting ducts are less permeable to water. This lowered permeability depends water absorption. So the concentration of urine produced is less than 1,200 MOSM kilogram and the volume is increased. The volume of this more diluted urine can be much larger than 1% of the filtrate formed each day. If no ADH is secreted, the osmolality of the urine may be close to the osmolality of the filtrate in the distal convoluted tubules, and the volume of urine may approach 20 to 30 liters a day, which is the same volume as 10 to 15 2 liters of soda bottles per day. So, in a healthy person, even when the kidneys produce dilute urine, the concentration of waste products in the urine is large enough to maintain homeostasis. Again, as with the production of concentrated urine, beneficial substances are retained and both toxic substances and excess water are eliminated. So, as you can see, this is the concentration of interstitial fluid and collecting duct with ADH and collecting duct without ADH. So, small volume of concentrated urine. In the presence of ADH, the collecting duct is permeable to water and the water is reabsorbed into the interstitial fluid. The result is a production of a small volume of concentrated urine and large volume of dilute urine in the absence of ADH. So, absent ang ADH. The collecting duct is permeable to water and water remain in the collecting duct. The result is the production of a large volume of dilute urine. So, when ADH is available, it increases the permeability of the collecting duct to the water. So, also, without ADH, the collecting duct is permeable to water.
Good day, ma'am. I am Christine Jan Bisabdullah, BSMT2. My topic is atrial natriuretic hormone. What is ANH or atrial natriuretic hormone? Is a hormone secreted by cells in the right atrium of the heart when they are stretched more than normal. Where is it produced? As we can understand by the definition, ANH is produced of atrium, hence the heart. Increased stretch of the right atrium occurs when blood volume is higher than usual. According to the figure, when the blood pressure is increased, the ANH also increases, which causes the sodium excretion and the water loss in the urine to increase. How ANH affects the urinary system? Atrial natriuretic hormone decreases blood volume through inhibition of sodium reabsorption in the kidney tubules. The ANH regulates sodium, which in effect decreases blood volume when it is higher than normal. ANH also inhibits AHD secretion from the posterior pituitary gland. Other notable effects of ANH, it is regulates ADH secretion. Last, increased ANH secretion increases the volume rather of urine produced, which lowers blood volume and thus blood pressure. So increased ANH is proportional to the urine produced that causes the blood volume to decrease and also decreasing the blood pressure in the process. Here, we can see the stages of how in ANH or atrial natriuretic hormone does its work. Stage 1. Blood volume is in the normal range. Stage 1, hence there are no signs of change. Stage 2, blood volume increases outside the normal range, which causes homeostasis to be disturbed. Stage 2, which initiate the process of homeostasis. Stage 3, the control centers respond to the change in the blood volume. Each organ and accessory organs that is responsible for blood pressure regulation is alarmed, thus reacts to the change. In the stage 4, the control centers cause ADH and aldosterone secretion to decrease, which reduce water reabsorption. The control centers also cause dilation of renal arteries, which increases urine production. The heart secretes ANH, which also increases urine production. And the stage 4, the organs respond to the change, thus causing this process. Stage 5, these changes cause blood volume to decrease. Stage 5, the blood volume slowly decreases. And lastly, the stage 6, blood volume returns to the normal range and homeostasis is restored. So stage 6, it is back to the normal range. Otherwise, this is the responses to a decrease in blood volume outside the normal range. So, homeostasis is disturbed, low blood volume induces lowered blood pressure, and the stimulus is triggered. Thus, the organs perform their respective jobs. Receptors and control centers are the blood vessels, heart, kidney, and pituitary. And the last, as a response, the effects are, or effectors, decreased renal blood flow decreases filtrate formation and less water is lost in urine, which increases blood volume. Increased aldosterone and decreased ANH increase sodium reabsorption in the distal convoluted tubule and the collecting duct. Less sodium and the water are lost in the urine, which increases blood volume. And lastly, increased ADH increases the permeability of distal convoluted convoluted tubule and the collecting duct to water. Increase ADH and also increases the sensation of thirst. Less water is lost in the urine. Finally, homeostasis is restored. That's all, ma'am, and thank you.
Hello everyone, this is Carrie and I'll be talking about the plasma clearance and tubular maximum. So firstly, the plasma clearance, which is the calculated value representing the volume of plasma that is cleared of a specific substance each time. So the plasma clearance can be calculated for any substance that enters the blood according to the following formula that is shown on the screen. It shows there that the plasma clearance is equal to the quantity of urine multiplied to the concentration of substance in urine over the concentration of substance in plasma. So for example, if the clearance value is 100 ml per minute for a substance, the substance is completely removed from 100 ml of plasma each minute. The plasma clearance can be used to estimate the GFR or the glomerular filtration rate if the appropriate substance is monitored. So this substance must have the following characteristics. So we have here four. First, it must pass through the filtration membrane of the renal corpuscle as freely as water or other small molecules. Second, it must not be reabsorbed. Third, it must not be secreted into the renal tubule. And fourth, it must not be either metabolized or produced in the kidneys. Now we have here the inulin. So for you to not be confused, it is different from the hormone insulin. So inulin is a non-physiological polysaccharide that has these characteristics, the four characteristics that I have mentioned from the previous slide. So as the filtrate forms, the filtrate has the same concentration of inulin as plasma. But as the filtrate flows through the renal tubule, none of the inulin gets reabsorbed, and thus the inulin gets steadily removed from the blood as it passes through the kidney. The rate of the inulin removal, called plasma clearance, is equal to the GFR. GFR is reduced when a kidney fails, and therefore the measurement of the GFR can indicate the degree of kidney damage. And so we have to remember that a high plasma concentration and a lower than normal clearance value of urea and creatinine indicate a reduced GFR and kidney failure. Plasma clearance can also be used to calculate the renal plasma flow, but the substances that must be used here must have these following characteristics. First, the substance must pass through the filtration membrane of the renal corpuscle. Second, it must be secreted into the renal tubule at a sufficient rate that very little of it remains in the blood as the blood leaves the kidney. As blood flows through the kidney, essentially all the para-aminohyporic acid is either filtered or secreted into the renal tubule. The clearance calculation for PAH is equal to the volume of plasma flowing through the kidney each minute. So in addition to all of these, the concept of plasma clearance can be used to help determine how drugs or other substances are excreted by the kidney. And a plasma clearance value greater than the inulin clearance value suggests that this substance is secreted by the tubule into the filtrate. Now we have the tubular load, which is the total amount of a substance that passes through the filtration membrane into the renal tubule each minute. And do you know that normally the glucose is almost completely reabsorbed from the tubule by active transport? but the tubule's capacity to actively transport glucose across the epithelium of the tubule is limited. So if the tubular load is greater than the tubule's capacity to reabsorb it, the excess glucose remains in the urine. And now we have the tubular maximum, which is the maximum rate at which a substance can be actively reabsorbed. So each substance that is reabsorbed has its own tubular maximum, which is determined by the number of active transport carrier proteins and the rate at which they are able to transport molecules of the substance. So let's say, for example, in people who have diabetes mellitus, the tubular load for glucose can exceed the tubular maximum by a substantial amount, and thus allowing glucose to appear in the urine. I have here a figure, so kindly look at it. On the upper left corner, you can see there the concentration of glucose in urine, and on the lower portion, you can identify or you can see there the amount of glucose entering filtrate each minute. So when the glucose is about or less than 320 milligram per minute, it means that no glucose enters the urine, and when the amount of glucose is 320 milligram per minute, it means that a small amount of glucose passes into the urine. So it's the concentration, or what we call as the tubular maximum, starts, and beyond that concentration, or when the amount of glucose is greater than 320 milligram per minute, it means that all glucose in excess of 320 milligram per minute passes into the urine. And so, as the concentration of glucose increases in the filtrate, it reaches a point that exceeds the renal tubule's ability to actively reabsorb it. And that's about it for my part. Thank you so much for listening, and keep safe.
Good day, ma'am. This is Alexishin Lapotahod, and for today I am going to continue the discussion regarding the urine movement. So first, let us discuss what is ureters, urinary bladder, and urethra. So ureters are tubes through which the urine flows from the kidneys to the urinary bladder. Urinary bladder is a hollow, muscular container that lies in the pelvic cavity just posterior to the symphysis pubis, while the urethra is which transports the urine to the outside of the body, exits the urinary bladder inferiorly and anteriorly. The ureters are tubes through which the urine flows from the kidneys to the urinary bladder. The ureters extend inferiorly and medially from the renal pelvis and exit the kidney at the renal hilum. So, the ureters descend through the abdominal cavity and enter the urinary bladder. The urinary bladder is a hollow muscular container that lies in the pelvic cavity just posterior to the symphysis pubis. The ureters enter on its posterolateral surface. In males, the urinary bladder is just anterior to the rectum. In females, it is just anterior to the vagina and inferior and anterior to the uterus. So its volume increases and decreases depending on how much or how little urine is stored in it. The urethra, which transports urine to the outside of the body, exits the urinary bladder inferiorly and anteriorly. The triangular area of the urinary bladder's posterior wall between the two ureters and the urethra on the urinary bladder's anterior wall is called as the trigone. So this region is histologically unique. The trigone does not expand with the urinary bladder wall as it fills. This causes the trigone to act as a funnel for emptying the urinary bladder. On the other hand, cystitis is an inflammation of urinary bladder which usually results from a bacterial infection. So, typically bacteria from outside of the body enter the bladder, which causes the infection by the bacterium of E. coli is the most common cause of cystitis. Transitional epithelium lines both the ureters and urinary bladder. transitional epithelium is specialized so that the cells slide past one another, and the number of cell layers decreases as the volume of the ureters and urinary bladder increases. The rest of the walls of this structure consists of the lamina propria, which is a muscular coat in a fibrous adventitia. The wall of the urinary bladder is much thicker than the wall of a ureter because it consists of layers of primarily smooth muscle, which sometimes called as the detrusor muscle. Contraction of this smooth muscle forces urine out of the urinary bladder. The epithelium itself ranges from 4 or 5 cells thick when the urinary bladder is empty to 2 or 3 cells thick when it is distended. The urethra is lined with a stratified or pseudostratified columnar epithelium. So, at the junction of the urinary bladder and the urethra, smooth muscles forms an internal urethral sphincter that prevents urine leakage from the urinary bladder. Pressure decreases in the renal tubules as filtrate moves along it during urine production. Hydrostatic pressure from filtrate average 10 mm high in the Bowman capsule and drops to nearly 0 mm high in the renal pelvis. This pressure gradient forces the filtrate to flow from the Bowman capsule through the renal tubule into the renal pelvis. Because the hydrostatic pressure is 0 mm high in the renal pelvis, no pressure gradient exists to force urine to flow through the ureters to the urinary bladder. However, the circular smooth muscle in the walls of the ureters undergoes peristaltic waves of contractions, which force urine through the ureters. The peristaltic waves progress from the region of the renal pelvis to the urinary bladder. They occur from once every few seconds to once every 2 to 3 minutes. So, parasympathetic stimulation increases their frequency and sympathetic stimulation decreases it. The peristaltic contractions of each ureter proceed at a velocity of approximately 3 cm per second and can generate pressures in excess of 50 mm high. Where the ureters penetrate the urinary bladder, they run obliquely through the trigone. Pressure inside the urinary bladder compresses that part of the ureter to prevent urine from backing up into the ureters. So the next preceding parts will be discussed by Ms. Tantenko and the other members of the group. That's all, ma'am. Thank you and God bless. Mwah.
This is Rosalian C. Tantenko, base MT2, and for today's video I am going to explain the flow of urine through the nephron and ureters. Next is the structure of how urine flow through the nephron and ureters. So this one. So waste ions and hydrogen ions secreted from the blood complete the formation of urine. So sa akong gipakita ganina nga structure, makita dito where the secretion happens. So first is the filtrate absorbed in the glomerulus flows through the renal tubule where nutrients and water are reabsorbed into capillaries. At the same time, waste ions and hydrogen ions pass from the capillaries into the renal tubule. This is what we call secretion. The secreted ions combine with the remaining filtrate and become urine. The urine flows out of the nephron tubule into a collecting duct. It passes out the kidney through the renal pelvis into the ureter and down to the bladder. Next is hydrostatic pressure. From filtrate average 10 mm of mercury in the Bowman's capsule and drops to nearly 0 mm of mercury in the renal pelvis. This pressure gradient forces the filtrate to flow the Bowman's capsule through the renal tubule into the renal pelvis. Next is the peristaltic waves or pressure. It progresses from the region of the renal pelvis to the urinary bladder. They occur from once every few seconds to once every 2 to 3 minutes. It is because The hydrostatic pressure is 0 millimeter of mercury in the renal pelvis, meaning no pressure gradient exists to force urine to flow through the ureters to the urinary bladder. However, the circular smooth muscle in the walls of the ureters undergoes peristaltic waves of constructions which force urine through the ureters. Next is parasympathetic stimulation. Parasympathetic stimulation, it is responsible for stimulation of rest and digest or feed and breathe activities that occur when the body is at rest. While sympathetic stimulation, it is where the nervous system directs the body's rapid involuntary response to dangerous or stressful situations. The peristaltic constructions of each ureter proceed at a velocity of approximately 3 cm and can generate pressures in excess of 5 mm of mercury. Where the ureters penetrate the urinary bladder, they run obliquely through the trigone. Pressure inside the urinary bladder compresses the part of the ureter to prevent urine from backing up into the ureters. So when no urine is present in the urinary bladder, internal pressure is about 0 mm of mercury. And even when the urine volume is 100 ml, pressure rises to only 10 mm of mercury. Pressure continues to rise slowly as volume increases to approximately 300 ml. But above volumes of 400 ml, the pressure rises rapidly. As you can see, urine flows through the nephron and ureters during the urine production. The pressures in the renal tubule decreases as the filtrate moves along it. To sum up, hydrostatic pressure forces urine through the nephron and peristaltic or peristalsis pressure moves urine through the uterus. That would be all. Thank you.
Good day everyone. By the way, I'm Erica Tanza. So for today's presentation, I'm going to discuss about the micturition reflex. But first, what is micturition reflex? Micturition reflex is a pathway that involves the integration of bladder filling, storage, and emptying of bladder with urethral sphincter contraction and relaxation. Basically, the micturition reflex is the neutral control of our urination. In the process of micturition reflex, our urinary bladder has a big factor. The urinary bladder acts as a reservoir valve for urine until it can be eliminated relatively quickly at an appropriate time and place. It means that the urinary bladder can stretch to hold a large urine volume. Its maximum volume can contain about 1 liter or about 1 quart of urine. But discomfort becomes noticeable when urine volume exceeds approximately 500 ml. So basically, our urinary bladder's capacity to distend is due to 3 factors. First, the wall of the urinary bladder contains large folds, it is similar to our stomach, which also unfold to enlarge the lumen. Second, the lining of the urinary bladder is the transitional epithelium, which it also stretch. And third, the smooth muscle wall of the urinary bladder, with the exception of the trigone, also stretches to accommodate fluid. So it only means that as urine enters the urinary bladder, it lifts and expands superiorly to accommodate the fluid. So now, these are the steps involved in micturition reflex. Micturition reflex is activated when the urinary bladder wall is stretched as urine fills the urinary bladder. So when the bladder is full, stretch receptors in the wall of the bladder send nerve impulses to the sacral region of the spinal cord. The urine filling the urinary bladder stimulates stretch receptors which it produce action potentials. These action potentials are carried by sensory neurons to the sacral segments of the spinal cord through the pelvic nerves. In response, action potentials travel to the urinary bladder through parasympathetic fibers in the pelvic nerves. By way of a parasympathetic response, signals return to the bladder and stimulate contraction of the muscle of the bladder and relaxation of the internal urethral sphincter. This part of the reflex is involuntary and is predominant in infants and young children. As the central nervous system matures, it acquires voluntary control over the external urethral sphincter. Basically, urination is controlled mainly by the micturition center in the pons. This center receives sensory signals from the bladder and communicates with the cortex about the appropriateness of urinating at the moment. At times, when it's not convenient to urinate, the center sends back an inhibitory signal to keep the sphincters closed and prevent voiding. But when you wish to urinate, this inhibition is removed. The spinal cord instructs the muscle of the bladder to contract and the sphincters to open to let the urine out. In overall, there are 6 steps in micturition reflex. First, we have the urine in the urinary bladder stretches the bladder wall. Second, the action potentials produced by stretch receptors are carried along pelvic nerves, which we can see here as the green line, to the sacral region of the spinal cord. Third, the action potentials are carried by the parasympathetic nerves, which we can see here as the red line, to contract the smooth muscles of the urinary bladder. Fourth, the ascending pathways carry an increased frequency of action potentials up the spinal cord to the pons and cerebrum when the urinary bladder becomes stretched. This increases the conscious urge to urinate. Fifth, descending pathways carry action potentials to the sacral region of the spinal cord to tonically inhibit the micturition reflex, preventing automatic urination when the bladder is full. Descending pathways facilitate the reflex when stretch of the urinary bladder produces the conscious urge to urinate. It only means that this reinforces the micturition reflex. And lastly, the brain voluntarily controls the external urethral sphincter through somatic motor nerves, which we can see here as the purple line, causing the sphincter to relax or constrict. Normally, the urge to urinate results from stretch of the urinary bladder wall, but irritation of the urinary bladder or the urethra by a bacterial infection or some other condition can also initiate the urge to urinate. If the spinal cord is damaged above the sacral region, no micturition reflex exists for a time. However, if the urinary bladder is emptied frequently, the micturition reflex eventually regains its ability to cause the urinary bladder to empty. Although a typical micturition reflex may exist, the person has no conscious control over its onset or duration, and this condition is called the automatic bladder.
So good morning, I am Serapia Tionas. So today I'm going to discuss all about the effect of aging on the kidneys. So aging causes the kidneys to gradually decrease in size. So as we get older, our kidneys decrease its size. So this decrease can begin as early as age 20. So, but becomes obvious by age 50 and continues throughout the remainder of life. So the decrease in kidney size appears to be related to changes in the blood vessels of the kidney. So the amount of blood flowing through the kidneys gradually decreases. So the amount of blood that is flowing throughout our kidneys also decreases. So starting at age 20, there appears to be an approximately 10% decrease every 10 years. So small arteries, including the afferent and the efferent arterioles, become irregular and twisted. So functional glomeruli are destroyed. So when we say afferent arteriole is a branch of the renal artery that brings in blood to the glomerulus, while the efferent arteriole is a branch of the renal artery that drains blood away from the glomerulus. So apparent arterioles maintain the blood pressure. So it is important because it maintains our blood pressure. So efferent arterioles maintain the glomerular filtration rate. So by age 80, 30% of the glomeruli are not functioning. So glomeruli is responsible for our blood filtrations. About 30% of the glomeruli that stop functioning no longer have a lumen through which blood flows. So other glomeruli thicken and assume a structure similar to that arterioles. So some renal tubules and collecting ducts become thicker, shorter, and more irregular in structure. So the function of renal tubule is any of the long narrow tubes in the kidney that concentrate and transport urine from the nephrons. So the capacity to secrete and absorb declines and whole nephrons stop functioning. So the kidney's ability to concentrate urine gradually declines. So eventually, changes in the kidney increase the risk of dehydration because of the kidney's reduced ability to produce a concentrated urine. So the ability to eliminate the uric acid, urea, creatine, and toxins from the blood also decreases. So an age-related loss of responsiveness to ADH and to aldosterone occurs. So the kidney decreases renin secretion and has a reduced ability to participate in vitamin D synthesis, which contributes to Ce2 plus deficiency, osteoporosis, and bone fractures. So recall that one-third of one kidney is required to maintain homeostasis, and the additional kidney tissues beyond this constitutes our reserve capacity. Therefore, the age-related changes in the kidney reduce the kidney's reserve capacity. So as the functional kidney mass is reduced substantially in older people, high blood pressures and atherosclerosis and diabetes have a greater adverse effect. So there is a disease that affects our kidneys. It is called the acute renal failure. So it is a sudden episode of kidney failure or kidney damage that happens within a few hours or a few days. So acute uh, acute renal failure causes a buildup of waste products in our blood and makes it hard for our kidneys to keep the right balance of fluid in our body. So acute kidney failure occurs when our kidneys suddenly become unable to filter waste product from our blood. So when our kidneys lose their filtering ability, dangerous levels of wastes may accumulate and our blood's chemical makeup may get out of balance. So there is a treatment for renal failure. So it is called the hemodialysis. So it is used when a person is suffering from severe acute or chronic kidney failure. So the procedure substitutes for the excretory function of the kidney. So hemodialysis is based on blood flow through tubes composed of a selectively permeable membrane. So blood is usually taken from an artery, pass through tubes of the dialysis machine, and then return to a vein. So as you can see in this picture, during hemodialysis, blood flows through a system of tubes composed of a selectively permeable membrane. So dialysis fluid, which has a composition similar to that normal blood, except that the concentration of waste product is very low. So flows in the opposite direction on the outside of the dialysis tubes. So waste products such as urea diffuse from the blood into the dialysis fluid. So other substances such as the Na+, K+, and glucose can diffuse from the blood into the dialysis fluid if they are present in higher than normal concentrations. So because these substances are present in the dialysis fluid at the same concentration found in the normal blood. So on the outside of the dialysis tube is a fluid called dialysis fluid, which contain the same concentration of solute as normal plasma except for the metabolic waste products. So as a consequence, the metabolic wastes diffuse from the blood to the dialysis fluid. So the dialysis membrane has pores that are too small to allow plasma protein to pass through them. And because the dialysis fluid contains the same beneficial solute as the plasma, the net movement of these substances is zero. And there is other treatment for kidney failure. It is called the peritoneal dialysis. So it is sometimes used to treat kidney failure. So the principle by which peritoneal dialysis works are the same as for hemodialysis, but the dialysis fluid flows through a tube inserted into the peritoneal cavity. So the visceral and parietal peritonia act as the dialysis membrane. So waste product diffuse from the blood vessels beneath the peritoneum across the peritoneum and into the dialysis fluid. So kidney transplant are sometimes performed on people who have a severe renal failure. Often the donor has suffered an accidental death and had granted permission to have his or her kidney used for transplantation. So the major cause of kidney transplant failure is rejection by the recipient's immune system. So acute renal failure has significant effects on other organ systems in the body, as this diagram illustrates. So it can affect the integumentary, digestive, respiratory, lymphatic, cardiovascular, endocrine, nervous, muscular, and also our skeletal system. So here in table 26.5, it is the representative diseases and disorder of the urinary system. So in the kidneys disorders, it has the inflammation of the kidneys and the renal failure. So in the inflammation of the kidney, first is the glomerulonephritis. So inflammation of the filtration membrane within the renal corpuscle, causing an increase in the filtration membranes, permeability, plasma proteins, and blood cells enter the filtrate, which increases urine volume due to increased osmotic concentration of the filtrate. And second one is the acute glomerulonephritis. Often occurs 1 to 3 weeks after a severe bacterial infection, such as the staph throat, normally subsides after several days. And third one is the chronic glomerulonephritis. It is a long-term progressive process whereby the filtration membrane thickens and is eventually replaced by connective tissue. The kidneys become non-functional. And lastly is the pyelonephritis. Often begins as a bacterial, usually the E. coli infection of the renal pelvis, which spreads to the rest of the kidney. The infection can destroy nephrons, dramatically reducing the kidney's ability to concentrate urine. And here in the renal failure, acute renal failure, and so in the renal failure can result from any condition that interferes with kidney function. So acute renal failures occurs when damage to the kidneys is rapid and extensive, leads to accumulation of waste in the blood. If renal failure is complete, death can occur in 1 to 2 weeks. And lastly is the chronic renal failure caused by permanent damage to so many nephrons that the remaining nephrons are inadequate for normal kidney function, and it can result from chronic glomerulonephritis, trauma to the kidneys, tumors, or kidney stones. So that's all. Thank you for listening.